Alright, so welcome to the first, the first class of topic 3 of CIE O-level chemistry syllabus, formula, stoichiometry, and the mole concept. So let's have a look at the syllabus first. The first thing the syllabus says is you need to state the symbols of the elements and the formulae of the compounds mentioned in the syllabus. I wouldn't worry too much about this if I were you, because this is pretty straightforward and simple, and I'll come to this later. I'll move on to the second outcome instead. So, deduce the formulae of simple compounds from the relative numbers of atoms present and vice versa. This isn't anything much complicated as well. It's just that when you in a compound, when you're said, for instance, in a compound, you're said that a compound contains like 2 hydrogen atoms and 1 oxygen atom. Pardon the crudity. Anyways, so you're asked to write the formula of this compound. So how to do it? So just note the elements you have. You got two elements here, hydrogen and oxygen. Just write them down. Then all you need to do is just write the number of atoms each element has respectively as their subscript. Like hydrogen has 2 atoms here in this compound, so you'll be writing 2 as its subscript at its base. And for oxygen you have 1, so you'll be writing 1 here. You're supposed to write 1 here, but we don't usually include the 1. If there's 1 atom of an element, we don't really include the 1 in it. We just leave it the way it is. So basically this formula denotes that this compound has 2 hydrogen atoms and 1 oxygen atom, and yes, you guessed it correct, this is just a formula of water, right? So that's pretty much it. The second outcome has been covered. Let's move on to the next. It says vice versa as well, so it's pretty simple and straightforward to deduce it. Nothing too complicated or difficult to catch. Let's move on to the third outcome. Deduce the formula of ionic compounds from the charges on the ions present and vice versa. Alright. So this basically, what this means is there are a lot of ions out there, right? For instance, there's the sodium ion, Na+, and then we have the magnesium ion, Mg2+, and then we have like the chlorine ion, which is Cl-, or like say for instance, let's go to a more complex ion like sulfate ion. Right. So how do you deduce the formula of an ionic compound from its respective by taking a look at its respective ions or charges? So basically what you do is you write as I said before in the second outcome, you write the elements, the elements you have, the components you have in this compound. You write them down first, and then see Na+ has a +1 as its charge, and Cl has a -1 as its charge. What you need to do basically is just cross multiply the charges with each other. Like there's +1 here, right? This +1 will move here, so it's 1. This +1 was here, this will just move here, it's 1. So in chlorine we have -1, so what you need to do is you just need to cross multiply this 1 here and bring it down to here, right? So we don't include the signs here, we just take the magnitude that's here, right? The charge, the amount of charge. So Na+, it'll just go down here, and Cl -1, we'll just take the value of the charge, and it'll be cross multiplied with Na, and from here it'll go here. So it's pretty straightforward. From Na plus 1 goes down here, comes down as 1, minus 1, the magnitude comes down here, becomes plus 1. So this is the formula of Na of sodium chloride. Wait, let's not go there. So this is the formula of the compound, which is formed by Na plus and Cl minus. But since, as I said before, we don't really include the ones, if any, so we'll just eliminate the ones. So this is the formula of the compound we'll be having, NaCl, and the nomenclature is like sodium chloride, right? Let's move on here. For now, let's see what happens when magnesium ion combines with Cl minus 1 ion, right? So as I said before, just write down the components first. Just write down the components first. Yeah. So as before, we'll just cross multiply the charges. So here it's 2, and on top of magnesium you got 2, so it will be cross multiplied and be brought to the base of chlorine. So here it'll be 2, and at chlorine we have 1 as the magnitude of its charge, and the 1 will just simply go from here to the base, from the top of chlorine to the base of magnesium. So as I said before, we don't really include the 1, so it'll be just this. Sorry, it'll just be, so it'll just be this, and the nomenclature will be like magnesium chloride. So if you're asked in magnesium chloride, how many chlorines do you have in per molecule or something, but how many atoms of chlorine do you have in magnesium chloride? So it's basically pretty simple. It's 2. So there are 2 atoms of chlorine here and 1 atom of magnesium here, right? So I guess that's pretty straightforward and simple. So the third outcome that we had about deducing the formula of ionic compound from the charges in the ions present and vice versa. Oh, I forgot to mention the vice versa stuff. Alright, so there's something else I forgot to mention, which is, let's consider let's have a look at what happens when magnesium combines with sulfur, or the sulfate ion, right? This is a sulfate ion. Let's have a look at what happens when magnesium Mg2 plus combines with SO4 minus. So as I said before, just write down the components of the compound. SO4. Alright, this is a pretty neat hexagon we have here. Anyways, so just write down the components of the compound we have here, and then just cross multiply the charges. So here we have, on top of magnesium we have 2 plus, so basically 2. On top of sulfate we have 2 as well. So we'll cross multiply. It'll become something like Mg2 from sulfate, from top of sulfate, and from top of magnesium the 2 will just come to the base of sulfate. So basically it's something like, when we have a subscript of something which already has a number in it, we include a bracket and then we write the 2, right? So this should be the formula of magnesium sulfates and magnesium and sulfate. So this should be the formula of magnesium sulfate, but this isn't. The reason being, when we have an equal ratio of atoms of each component, we tend to cancel them out. We tend to write them in the most simple form possible, Right. So the most simple form possible of this compound is just eliminate the 2's. Like here's a 2 and here's a 2. The ratio is 1:1. So we decide to simplify it down to magnesium Mg and SO4. So see, when you remove the 2, you don't really need to include the bracket. So basically the theory is, when you have an equal ratio, when you have the same ratio of atoms in a compound, you can simply remove it and bring it down to a 1:1 ratio. Bring it down to a 1:1 ratio. So that's it. And the vice versa stuff. See, for instance, when you have NaCl here, since the ratio is 1:1, it's pretty apparent that it's pretty obvious that there must be a +1 here and a -1 here, since the ratio is like 1:1. So yeah, that's that. That's just what they mean by vice versa. Alright, so we're done with the third outcome. Let's move on to the fourth. Interpret and construct chemical equations with state symbols, including ionic equations. Alright, so let's clear the screen first. Interpret and construct chemical equations with state symbols, including ionic equations. It's alright. So it's pretty simple to say. For instance, when sodium, right? When sodium, I don't think it's, when sodium reacts with, say, hydrochloric acid, HCl, the product is like NaCl and plus water, hydrogen. So how do we balance it? Since there are like 2 hydrogen atoms here, we must make sure there are 2 hydrogen on the, basically you need to equate your both hand sides, right? Your right hand side must be equal to your right hand side must be equal to your left hand side. So the number of total elements on the right hand side must equal the total number of elements in total number of atoms in the left hand side. So basically there are 2 atoms of H here, so there must be 2 atoms of H here as well. So when you do this, you end up having 2 atoms of chlorine on your left hand side. So to balance it, you must add 2 atoms of chlorine here as well, which you do like this. And since you have 2 atoms of sodium or Na on your right hand side, you must have 2 atoms of Na or sodium on your left hand side as well. So there we go, a balanced equation. This is a subscript, by the way. This isn't a coefficient or anything. This is just a subscript. Alright, so that's that. And moving on to ionic equations. So basically, like Na, right? So how does Na become, or how does Na turn out to its ionic form? Like, what's the ionic form of a sodium? Na plus, right? So how does sodium or Na become Na plus? It's simple, just by releasing an electron, right? Which you learned before. So how Na becomes Na plus is pretty simple. Just like Na will lose an electron. So basically minus, I'm denoting electron by E to form Na plus. Na plus. So we don't write it this way, we tend to write it on the other hand side. So Na will just be equal to Na plus plus, I better include it in a bracket, Na plus plus electron. So basically it was what was a negative, what was negative here on the on the left hand side will become a positive here on the right hand side. It's simple mathematics. So yeah, so this is it. And for instance, the second ionic equation, for instance, let's consider the ionic equation of chlorine, right? So chlorine is basically Cl2 in room temperature under standard conditions. So how does it become Cl minus, right? It'll just gain electron, right? So since chlorine exists as Cl2 under standard conditions, so there must be two atoms of Cl, two ions of Cl minus must be formed at the other end, which means that if one chlorine atom gains one electron from to become one chlorine ion, two chlorine atoms must gain two electrons to become two chlorine ions, right? So simplifying it, Cl2 will basically become 2Cl minus by gaining 2 electrons. So Cl2 will be gaining 2 electrons to form 2Cl minus, right? So now the question is, how do we come to a reaction from these two equations? How do we form a complete chemical equation from these two equations, right? The trick is you need to balance the number of electrons first. So basically there are 2 electrons here, but there's just 1 electron here. So what you need to do is you need to make this electron 2, or you need to make this electron 1. So I'm going for the first option. I'll be making this 2. So in order to make this 2, you must multiply the entire thing by 2, right, to balance your right hand side and left hand side, as I said before. So 2Na will give 2Na plus by losing 2 electrons. Now the number of electrons is balanced, right? Now all you need to do is combine the right hand sides with the left hand sides of both equations. For instance, on the left hand side we have 2Na on the first equation, and the second equation we have Cl2 plus 2 electrons. You'll combine all the right hand sides, you'll bring all the right hand side elements together. So on the right hand side of the first equation we have 2Na. We'll combine it with the left hand side. On the left hand side of the first equation we have 2Na. We'll just combine it with the left hand side elements of the second equation. So we write 2Na, and then we combine it with the left hand side elements of the second equation, which is Cl2 plus 2 electrons, and then we combine the left hand sides of both equations simultaneously, the right hand sides of both equations similarly. So 2Na plus 2Na plus, alright, the bracket again, 2Na plus plus H2. So my bad, 2 electrons. So the right hand side of equation 1 we've written, and we'll just add it with the right hand side element of the equation 2, which is 2Cl minus. Right, so we just combine both right hand sides and left hand sides together. So now see, here's 2 electrons on your left hand side, and here's 2 electrons on your right hand side, right? We can eliminate both, right? We'll just eliminate both to make things simpler, right? So this is our final chemical equation. this will be our final balanced chemical equation. You don't need to balance it further since you already did it. Since you did it already, like when you balance the number of electrons, and so this is basically your final equation. This is basically your final equation, a balanced equation. So yeah, that's it. That is how you balance an ionic equation. All right. So, so we've just covered the fourth outcome of our syllabus. Now let's move on to defining relative. Oh, there's something I missed with state symbols. You must include the state symbols. For instance, sodium is a solid at room temperature under standard conditions, so you'll be just including the S here. And in case of ions, bear in mind that ions are mostly in aqueous state, so just mention aqueous. Electrons don't really have a state, so never mind that. So Cl2 has a gas at room temperature, so you'll be just writing Cl2G, and in the main equation you'll just include the state symbols just like you've written in your ionic equations, the final equation I mean. So yeah, that's just that. I don't think you need to include this here, just keep the ion safe. So yeah, that's it. If you want, you may just include the aqueous parts, but I don't think that's compulsory or anything. So yeah, this is your final equation, including state symbols and all. So we've now fully covered the fourth outcome of our syllabus. Let's move on to the fifth, defining relative atomic mass AR. So this will take some. This isn't. All right, never mind. So let's just. Right. So let's consider the periodic table. Let's have a look at our periodic table first. Do we have a periodic table here? We should. There's supposed to be a periodic table here. There we go. Oh boy, it's tilted, so I hope you'll take the effort of tilting your head and reading it out. So anyways, so here we see the key here is given: atomic number, atomic symbol, name, relative atomic mass. So since we're studying relative atomic mass, we'll just go for it. So relative atomic mass is at the down right bottom of each element. So basically the relative atomic mass of beryllium is 9, the relative atomic mass of lithium is 7, sodium is 23, magnesium is 24. So the relative atomic masses of elements are the bottommost number that you have underneath every element. So calcium is 40, potassium is 39, and so on. So all that said, what is a relative atomic mass, right? So basically these elements, as you understand that atoms are very small, right? So you can't really weigh their masses, or you can't really calculate, or you can't really find their masses using traditional experimental methods, right? So what you need to do is you need to bring up something. What scientists did is, what they did is they just brought up something to compare. The masses of other elements, right? Does that sound very critical? I'm sure it does. So basically, what the thing is, for instance, in a classroom, there are like 25 people, and you don't really have a perfectly calibrated weighing machine to weigh each of their masses. So what you do is you take the lightest student, you take the most lightweight student available in the class, and you take a rough reading of his mass. Say it turned out to be I'm pretty bad at approximating, so say it turned out to be 40 kilograms, right? So this is the weight of the smallest kid, of the most lightweight kid in the class. So what you do is, you don't really weigh or measure the weights of, or measure the masses of the other students individually. What you do is you compare their masses to this kid. For instance, the heaviest person, the heaviest student, the heaviest kid in the class weighs 4 times as much as the lightest student. So basically, the heaviest student is 160 kilograms, which is scientifically impossible. I won't go to details. Anyways, so yeah, the heaviest guy in the class weighs 4 times as much as the lightest guy in the class, right? So basically, it's 4 into 40, right? So basically, let's consider that the lightest student in the class weighs X kilograms, and the heaviest is hence 4x, right? And the others, the remaining 23 students, will be measured, the weights of the masses of the remaining 23 students will be written down, or will be calculated, or will be approximated similarly in a similar process, right? So one might be 1.5x, one might be 2x, one might be 0.5x, one might be 0.75x, and so on, right? So in a periodic table, the relative atomic masses are compared exactly in the same process. So how exactly? Just a moment. See, what we did here is we took the lightest student in the class and then compared his weight to everyone else's, and then calculated their relative weights, right? Relevant masses, right? So here, in case of the elements, what scientists did was similar to what we did. They took the mass of they took the element called carbon, which has atomic mass of like 12. This 12 is this 12 is the 40 kilograms we had obtained, remember? All right, so what scientists did is they divided this 12 to 12 parts. So they considered that this mass can be divided up into 12 equal parts, and each part will have an equal mass, right? So a uniform distribution of mass. So basically, when you do that, each part will have a mass of like 1, right? So 1, 1, 1, 1, 1, and 12 ones, and you get 12, right? All right. So basically, how much will one part weigh? What will the mass of one part be if you divide 12 in 12 parts? It's simple, 1 by 12, right? So what scientists did is they considered this as a factor to use while calculating or approximating the masses of other elements. For instance, let's have a look at sodium, right? Sodium is 23, right? So 23 means that actually this 23 is 23 times of 1 by 12 of this mass. When we have calcium, of 40, it basically means calcium is 40 times as heavy as 1/12 of the mass of this carbon. I hope I'm clear enough. So let me go through that again. Carbon, you take an element, carbon, to compare its weight, compare its mass to everyone else's, to draw a fair comparison or something, and then you divide its atomic mass into 12 parts, 12 units. Take the mass of 1 unit and use this 1 unit to compare or to approximately bring up the masses, to bring up an approximation, a rough approximation of the masses of all the other elements present in the periodic table, right? So when you have 23 in sodium is an atomic mass, it basically means it's 23 into 1 by 12 of the mass of a carbon 12 atom, right? When you have 40 of calcium, you basically have, it basically means you have 40 into 1 by 12 of the mass of a carbon 12 atom, right? So it's pretty simple as that. So yeah, that's what relative atomic mass means, simply. So now we need to have a definition, right? What are we going to write in our exam paper? What are we going to answer? How are we going to answer the question of define relative atomic mass, right? So it's pretty simple. Relative atomic mass is the average mass of an atom, of an element, compared to 1/12 the mass of carbon 12 isotope. I repeat. So the relative atomic mass is the average mass of an atom of an element compared to 1/12 the mass of a carbon 12 isotope. This is a standard definition of a relative atomic mass, right? So I hope that's clear. And so we've just completed the 5th outcome of defining relative atomic mass, and well, we'll just leave it here and complete the rest in the next tutorial. So yeah, I hope this helped. That's it.